Okay, thank you, Costas, for this introduction again. And in the last lecture, I'll write down, this is the plan I have. So I'll quickly show you, if you remember, in the first lecture, we discussed about Bell states, pure states, some. So I'll show you quick code if you want to use these things in your research or in your explorations. So I'll just show you a very useful tool, which is QTIP, which is quantum toolbox in Python. So you can do all sorts of partial traces, von Neumann and things like that with the states or density matrices. Then I'll move to defining the fundamental or the initial tensor, which we start with in the 2D easing model. And then I'll show you diagrams, which I have, like I just pulled it out from one of the papers, basically. And I'll show you a diagram because last time I was trying to draw it and it's not very nice to draw it live. So it will become more clear what we mean by one step of coarse graining, or what we mean by how do we block the tensors, basically. And then we'll go to the code to do the same thing. So first we'll see it on a diagram in terms of tensors, and then we'll write the code for that. And then once we have the initial tensor, we have one step of coarse graining. Then I'll show you how to do 2D classical easing model. And then depending on how much time we have, and if everything before is clear, we'll go to the extensions to say Q state POTS model, which is like a higher generalization of easing model to admit more than two states at every given site. So for example, instead of up and down, it can be in 3 states, 4 states, and so on. And then once we also cover that, then I'll eventually go, if we have time, to the SU2 action, Wilson action. You might not know what Wilson action is. I'll explain what Wilson action is in lattice gauge theory. Then write the initial tensor for the Wilson action, and then show you that you can still do things we learned for simple cases to say more complicated field theories. So that is the initial plan. Before we do that, I just want to point out this very nice review article on tensor networks, which is also, I think, a Springer book. So this is just to show you the construction of the initial tensor, which we'll consider. So for example, just consider right now, here we have a 2x2 configuration of spins, which can either be up or down, for example, and they can be labeled by S1, S2, S3, S4. So based on these 4, you construct one tensor, which is shown up here, right? So based on this 2x2 lattice, you go to the dual picture, you have this T, where you have 4 bonds, which are not the physical interaction, because the physical interaction is red, which is shown here. You go to this dual picture, define this T, and once you have this T, you can consider, for example, more spin squares like this. You can consider, for example, if you have 3 along horizontal, 3 along vertical, you can write 4 T tensors from that. And this will now become the basic unit cell, or the stuff we'll take, and then we'll combine it several times like this to get to some thermodynamic limit. Now, the whole point of this is that we have to go from this spin degrees of freedom, which is the physical system, to this description of T. And that is what I call the construction of the initial tensor. So going from these S to T is what we'll see in the code. That how do you, it's very straightforward. There's nothing. So you just have to know that the partition function, for example, is defined as, say, beta times Si, Sj, all combinations of that, right? So you take these two, and then take all the possible combination, whether they are equal to 1 or whether they are equal to 0, right? And based on that, you have to define this as a tensor network, and that is exactly what we'll do. So as I said, it's just the Boltzmann weight decomposition. So once we have that, then we want to coarse grain those tensors, right? So suppose from this entire thing, decomposing of Boltzmann weight, we have one of these tensors, T, right? So at the end of this, we have one tensor, T. Now, if we take that tensor, so this is from some recent, last year we wrote a paper, and this figure is from that paper, because I was trying to draw this the last time, and it was probably creating confusion. So it's better to use this figure. So we have this tensor T, and then The upper panel is along one direction, the lower panel is along the second direction. So you start with that T, combine 4 of them together, and do a contraction like this. So for example, take 4 copies of this tensor, combine the legs, and leave 4 of the legs open or dangling indices, I, J, K, L. And then you do a SVD. And then based on what is the size of this matrix and what is the size of the singular values you get, you truncate or not truncate. As we discussed in the previous lecture, up to 3 steps of coarse graining, you need not truncate, because initially the tensor is just 2 to the 4, it goes to 4 to the 4, it goes to I think 16 to the 4. So you can just keep those things exact, but after say certain number of coarse graining, you have to truncate. So based on that, it truncates or does not truncate, and then you get this U matrices here. And then based on that, and these are the singular values. So this is U and these are the singular values. So I just write it like a rank 3 tensor. And then I combine that thing like this. So I have 2 tensors here. I have 2 objects from the SVD, and I combine them like this. So they still have 4 indices free. And that gives me this new tensor, which is T twiddle IJKL. So this is along one direction. Now you want to take this tensor and go to the lower panel. And once you go,
I think maybe your cursor is not very visible. Is there some way maybe to?
Is it visible? Oh, wait, let's see.
To make it permanent or something.
Can you see it now?
Yeah, yeah.
Okay.
But I think you need to press on it. It's not always on. It's always when you press.
Okay. So
yeah,
but initial tensor, then you have 4 of these together, combine 4 of these together, do a SVD, construct U, and then combine those U's with the tensors which are here to get another tensor, which is lower in color, right? So this color is a little lower than this because you might be throwing away some singular values, so it might not have the same information. Once you have this, you go to the lower panel, which is along the second direction. You do everything like you did before, but flipped by pi by 2 or 90 degrees. So what was free on this side now is free on the upper legs. What was contracted like this now is contracted like this. And this gives you a completely new tensor, which is T1. This upper panel plus lower panel is 1 step of blocking or 1 step of coarse graining. If you do n such steps, or for example, if we have done n for 1 already in these 2, if you do n minus 1 more iterations of this, the same thing, you do a total of n iterations, you go to a tensor which is Tn, and then you combine them like this. So you contract all the indices, and this gives you a partition function approximation. And once you have these, you can compute anything you want to do. For example, you can compute free energy, internal energy. You can look at the specific heat. For example, this is just computing the network, right? This is just computing the partition function. How we compute any observable. So for example, you want to compute, for example, a magnetization for Ising model. You want to compute, say, some Polyakov loop for a gauge theory, SU2 gauge theory. The way you do it is you construct the partition function, and then you want to compute some observable. So what you have to do is something like this. This is computing the denominator. Now, the way we compute the numerator for some observable O is that we do the same coarse graining like we have done in this case, but we change one of the tensors. So we introduce an impurity corresponding to that observable, and then we compute the expectation value of that observable. So more details can be found in this paper and other papers, but there's a way to compute Z, and there's a way to compute O twiddle Z, where O can be, say, sigma Z, or it can be a Wilson loop. So that is how we compute expectation values in any calculation, like even in lattice.
So Raghav, is there can I call this like a prescription for blocking? Like, and there's some other prescription I can come up with.
There are tens and tens of prescription of blocking. So this is not the only one. This is one which I'm showing, which works fairly nicely. If you go to higher dimension, there's different ways of doing things. And everyone, like, there are certain, at least in 2 dimension, there are 4 or 5 nice ways of doing it. In 3 dimension, there are 2 or 3 ways of doing it, and so on. So this is a prescription. Yes.
And I mean, okay, you're showing it in like 2 steps, right? But could I have combined them into one? Like, I mean, when I put these 3-point tensors there, I mean, they're just in one go. Is it just for clarity that you're doing it?
Yeah. In like this is one step. I'm just showing that it is along different directions because we are in two-dimensional square lattice, so we have to block along both the directions. So I'm showing you. So for example, if you say that, oh, I don't want to construct this object Z, but I want to construct a transfer matrix, right? For transfer matrix, you just want to block along one direction, then take a matrix product along the time slice, right?
Yeah.
So in that, you can just do the upper panel and get the transfer matrix or something.
Okay, so this is specific for the partition function.
Yes. So transfer matrix, you just do the upper thing. I just wanted to clarify is that you can also just slice along one of the direction and then do the transfer matrix stuff. So for example, Z can also be approximated by trace of the transfer matrix times the number of slices. So this can give you transfer matrix if you say that, oh, this is along one direction. You don't need to do the second one.
But there are 2 steps where you've approximated, right? You're approximating the horizontal and when you do vertical, right?
Yes. Usually we choose it to be the same, but yes, that's right.
Okay. Is there any questions?
Okay. Are there any questions now? Because right now, now after 10 minutes or so, what we'll do is we'll just write a small 10-line code to do this diagram, nothing else. And all this, if you want to look at the code, I'm not going to send notebooks because all the code is open source. All the papers we write, we put the code online on. So you can go to this paper, you will find codes online, you will find this, and the GPU stuff, everything is online and in these papers. So it's not some secret knowledge. You can, if you want to explore, you can explore it. Okay. So with that said, let me go back and now open Colab and show you a couple of things about Qtip very quickly, and then move to say doing these tensor stuff. So for that, if you are doing it, I'll just open Google Colab and then share. Okay, so yes, let me share. So first of all, we need this Qtip. So I'll quickly install it here. So Qtip is very useful if you want to play around with any of these things. So, you'll see what I mean by what you can actually do. It's very powerful. In fact, you can also use it for if you want to deal with Wigner functions, if you know what that means or what have encountered that. You can do Wigner functions, you can do a lot of partial traces. It's very nice to explore multipartite entanglement scenarios and see what are the possibilities, because it's difficult to do these things by hand, obviously. Once you go to 5-6 qubits, the partial traces can become very complicated. So yeah, this is just a nice tool people have developed. So we install these things, then so yes, we want to create a ket to DM. That means we want to create a Bell state. So for Bell state, we can just write it like this, and the state is 0, 0. So for example, I'm creating the first Bell state. As you know, there are different combinations. So this is 0, 0 plus 1, 1 square root of 2. I'm creating that Bell state, and I'm changing that state into a density matrix. So going from ket to density matrix. And then I want to compute rho square, which is rho times rho. Then the trace of rho is equal to NP rho trace. So we're taking a trace. So we're creating a Bell state, creating a density matrix. What I want to show you is a Bell state is a pure state. And to show that, I have to show you that the trace of rho is equal to trace of rho squared is equal to 1. So for that, we do this. So rho dot full, and then trace rho square is trace rho square of full, and then print trace of rho square, right? So let's, hopefully this will work. Okay, so what it does is it creates a Bell state, computes a trace, and both of these are equal to 1, right? So now that means that this state is pure. For example, if I construct a random density matrix, for example, let's see. So rho dm is equal to random dm4. If I consider a sorry, yeah, so rho dm, was it from my side? No, I don't think so.
No, there's echo from the room.
Okay. So what I'm now going to show you is that for random density matrix, the trace is not equal to 1 because it has to be less than, remember that for the maximally mixed state, the trace of rho squared is 1 over d, where d is the Hilbert space dimension. For a generic state, it can be any number between that and 1. So for example, if I run it once, I get 0.45. I run it again, 0.57. So these are all example of mixed, they're example of mixed density matrices or mixed quantum states because they don't have rho squared equal to 1, right? And trace rho squared deviation from 1 is also a measure of how impure the state is. So for Bell state, there's no deviation, so that means pure, and so on. So for example, you can do, sorry.
Is this a 4-spin state, or what is the?
Yeah, so no, this is a density matrix of size 4 by 4, so 2 spin.
4x4. Oh, 2-spin.
Yeah. So let's see. Yeah, so this is a 4 by 4 matrix here.
Oh, okay. So a random 4x4 matrix.
Yeah, random 4 by 4 matrix. So a random density matrix corresponding to 2 spins. Yes. So you can do a lot of things here. You can also compute the von Neumann entropy, for example, if you want to do. So for example, one of the things you can also do here is you can do partial trace. So for example, let me see if I can quickly write down. So rho A, for example, can be rho dot P trace. So rho dm dp trace 0. Yeah, so this is a 2, so I can trace over one of the subsystems. So this gives me some rho A. So let's print rho A. Oh, rho A is like this, sorry. So now, for example, let's not print this. Let's just print this. So rho A is not this object here. And if I can do 0, 1. So yeah, you can do these partial traces over the subsystem. So for example, if it is 2 spins, so HA cross SB is 2 by 2, you can trace over one of the things using this command, and then you can compute the objects like this. So you can do a lot of things, and then you can compute a von Neumann entropy for this rho A, for example, and that is another one line. So this is a useful tool, but yeah, let's not go more into this. This just wanted to give you an idea about how to do these computations, which we saw in matrix product state and things like that. So this is the usual toolbox to do those things. What we want to now do is go to the so is there anyone who is coding live or like there in the room? Like, is there anyone who's doing things?
Yeah, there is one. Yeah, there are a couple of people, I think. Yeah.
A couple of people? Okay, okay. So if that is the case, then let's pip install an object which we'll need now to do the contraction. So this will take some time, but we can install this. Pip install, yes, let's pip install this. So while this is installing, I go to the next cell, let it happen in the background because I think this takes little time, about 1 minute. And what we can do then is write down the tensor network stuff for the one step of coarse graining which we saw. Yes, so let's see, just a second. So yeah, is there a way I can share both the figure and let's see. Okay, maybe let me just code now and then. Okay, so the first thing is we define some coarse graining function, which will do one step of coarse graining along both the directions. And let's see, say that we define some 4-index object as T4. And then we do contract of, I'll write down the indices, then explain in the figure. I'll show you in the figure what I mean by. Okay, so this is the step where we combine 4 tensors together. So let's go back and see if we can see the. Do you see the iPad or do you just still see the Google Colab?
We only see the Google.
Okay, so okay, I have to stop share and then reshare, I guess. And this is going to be a headache. So right now, what we are trying to do is we are in this step. So we have initial tensor, which we define as Ti in the function. And then we take 4 Ti's together. And then we are writing the indices. Note that the indices of the first one is JA something something. The second is I, that same something, which is on the lower index of this object. And in this leg and this D, right? And then you have 4 of them. And at the end, you're left with IJKL, right? So that is the initial. So if that is the diagram, then the corresponding code for that is this. At the end, I'm left with 4 indices IJKL. I started with 4. So the notation I'm using is that you start from the west, north, east, south notation. So JABE. And then you see that the third index is the one which is contracted with the third one of this. And then you have this combination. So this combination gives you something like this. Note that when you see the figure, you'll see that the right side, we are not, the figure is simplified in the sense that we are joining the east tensor of the left side with the west of the right side, but it's the other way around. So for example, so this tensor is numbered as now when we go to the other side, sorry, I don't know what is happening. Yeah. So these are the two things. And then for this tensor, I have L, A, B, F, T, K, F. Say this is G, G, D. So in the diagram, for this case, I'm going along this direction for the indices. In this case, I'm going like this. And that's just because I want to simplify the notation, because the actual contraction happens between these two bits. So it's the east of the first and the east of the second, but I can contract the east and the west and change the writing of the indices, but it doesn't matter. You can try both of them. It will give you the same result. So this is one step. Is there anything which is not clear at this point? Because I'll go to, like, I'll just do SVD now, then attach the result output of the SVD to two of these tensors and construct a new tensor. And then I'll take 4 copies of the new tensor, do a SVD, attach SVD, and find a new tensor. So there's going to be 10 lines. So this is line 1, line 2, line 3, line 4, line 5, line 6, literally like that. One arrow is basically one line.
Okay, I don't see any questions right now.
Okay. So keep going. So this is the first step. By this time, if you are doing it live, it will have installed this. This is a package which does tensor contraction better than the einsum. So we saw einsum. This is an optimized einsum using some PyTorch. So PyTorch is a very popular machine learning routine or software package, and it helps us because using PyTorch we can do tensor contractions faster, right? So I'll just now go a little faster because now you understand. I'll just copy these things here, from here to probably here. And this is T, so I'll make everything is T. So this is Ti or T. So this is one step of coarse graining, right? Let's come back to this and have one more look at it. So this is the first step. This is the second arrow where I do a SVD. So how do I do a SVD? I take this object and then I combine the first and the second index together, fuse both of them index together as we discussed, fuse the second and the third together, and then I say some decut. Now note that this decut is the bond dimension. So we'll see later what this decut, how this decut is selected, but just for right now, just assume that this is some number decut which we set in the numerical computations, and then from that we get this U. So this routine usually gives you U, S, and V, but we just want one U, which is the U from this, and we attach it to two of the tensors TT using the contraction pattern which was shown in the diagram. And this gives you the end of first step, end of first direction, and that is Tx. Now you take 4 of those Tx together, contract them, do the same combining of the tensor. Now note that I'm still using 0, 1, 2, 3, but I moved these indices together. So I said that for the first case, you have to go along one direction, then you go along the top direction. But this is kept same, but this is now different from this. So this is the second step. Once we have that you combine them with the tensors you got from the end of the first direction step, and you combining them like this to get a new tensor, which is Txy. Then what we do is we look at Txy and look at the maximum element of that tensor and divide. This is like norm division. So we divide by norm because we don't want the tensor to grow. Like if you don't divide by the norm, it just like you need to have like it grows quickly. So we divide by norm at each step and keep that norm into some dictionary so that we can use it at the end, because these norms will be useful to compute free energy, for example, at the end, because these have information about the Z, right? So we don't want to carry this norm, but we have to store them somewhere. This can be the maximum element of the tensor. This can be the Frobenius 2 norm. This can be one norm. This can be anything. It doesn't really matter, but you have to do it consistently in every step. So compute the norm, which in this case is just the maximum element. And then you divide the yes.
Yeah, so the range of indices of Tx is not the same as T4, right? Each index, like A, I, B, C, like it's twice or something, right? Or am I confused?
So it depends. So we'll start with everything going from 0 to 1.
Yeah.
Right. And then in the second step, everything goes from 0 to 3, then 0 to 7, then 0 to 15, and so on. But at some point, it will be truncated. And then
so the code is smart enough. The code is smart enough to know this. So when you say contracts, it contracts over the allowed range of indices. You don't have to tell it.
No, so that is what I'm going to show. Yeah, it is smart enough. It is smart enough because there's something in SVD which I have not shown yet, which will keep a track of the minimum. So it will all, yeah, we'll come to that. Good question. So we'll come to that. So this is one step of coarse graining here, and then we output the coarse grained tensor and the norm, right? Now, one of the important things in this routine, for example, is this SVD which we are doing. So let's just copy SVD from this chunk of code and look at it closely. It's the usual SVD, but I have my own routine in SVD, which you can find in that paper. So basically what it does, it has 4 inputs.
Could you put this in the chat for people who are...
Oh yeah, that's right. Okay.
Maybe it's too long, but yeah.
Yeah, that's why no, it's okay. It went. Okay, fine. So yes, maybe I can. Yeah, let's just not put this one right now. I just put SVD because I'll put the entire code later. So let's look at SVD. What it takes. There are 4 arguments it takes. It takes the tensor. Then you have to specify which indices you want to fuse, and they will become the left indices. And then you have to specify which indices on the right you have to fuse, which is the other matrix index. And those are right indices. And then there's a D. Now, what Costas was asking is happening somewhere around here. So let's say, let's remove this line because this line is not removed. Is happening along this line. So once I throw it some tensor and the matrix it composes out of it, it does SVD and does everything. And then I ask it to tell me the size of, say, U. So suppose it tells me after first step of coarse graining, it will tell me that the size of U is some 4 by 4 or something like that. At the second step, 8 by 8, 16 by 16. And I tell it to choose a D, which is minimum of the size of the U and the D. And this is the bond dimension D. So whenever it sees that the size of the U from the SVD is larger than the bond dimension, it truncates. And this is what this step is doing. Keeps only highest these singular values or eigenvectors corresponding to that. And this is the notation we use in Python. That if you want to truncate, so this is an array, you take everything on the second side, but you truncate this index up to D. And if D is, say, for example, larger than the size of the U, then it doesn't truncate, obviously, because it's exact. So this is the usual routine to do that. And now with the coarse graining and the SVD done, we'll go to the third element which we need is the construction of the initial tensor. So let's go to construction of the initial tensor. And then we put together everything and then we'll run the code. So for example, I'll just take this chunk here and put it here. So for example, these some tests I was doing. So one of the things is that the initial tensor is not unique. There are different decompositions you can make based on how you factorize the Boltzmann weight matrix. So first you have to construct a Boltzmann weight matrix. Boltzmann weight matrix is, for example, for Ising spin is just 2 by 2 matrix because there are 2 states or the possible values of spins and there are 2 neighbors, right? Now, if you have more states, for example, then you have to consider a higher Q by Q matrix, something like that. So in this case, this 2 by 2 matrix, and I'll define beta as the inverse temperature, H as the magnetic field, which I'm setting 0, but for general, you can also set H to be some general value. And this is tau. And once I have tau, I construct this matrix, or equivalent representation is the one given below. So basically, when the spins are both 1, you have a factor of exponent of beta. When the spins are either 1 or 0 or 0 or 1, there's a factor of 1 because e to the 0 is 1. And this can also be used. So once you have this W, which is a 2 by 2 matrix, you can take a square root, or you can do a Cholesky decomposition, which is basically equivalent to the square rooting of the matrix, basically. So you have a W matrix, which is the extension, as we saw, one of the legs. But note that every link is going to be shared by 2 spins, one on the left, one on the right, right? So you don't want to overcount or over specify the weight. So that's why you take a square root of that. And this is what this is doing. Once you have the square root of that, you just combine it like this. So the simple notation, WIA, WIB, WIC, WID. And this gives you the tensor, which is out. So out is the initial tensor for the easing model. Now, if you go to a complicated model, say XY model or O3 model or O4 model or SU2 gauge theory, this thing will change drastically. It's not any simple anymore. The indices in this case, or the matrices in this case, are 2 by 2 matrices because this is a discrete Z2 symmetry. If I was doing this for, say, a model which has continuous symmetry, for example, O2 model, then these indices will run from minus infinity to infinity. And then you have to truncate right at the start, in the sense that you have to truncate already at the initial level. But in easing case, you can exactly do the initial decomposition and also 3 steps of coarse graining because the size of the tensor is less. But for any continuous symmetric global symmetry system, we have to truncate right at the outset. And that often creates a lot of problems, and there are a lot of work trying to understand how to do those truncation and what to and how to write an efficient initial tensor for those cases. So this is what we did do here. And now we have all the parts we need. We have one step of blocking. We have the truncation in terms of SVD, and we have the initial object which we want to block, right? So now what we can go do is, let's see. So now what we can do is I'll have this big code, which is which I'll explain, but most of the parts we already understand because okay, so let's just paste this code now and go to the top. So this is both the CPU and the CUDA. CUDA is just when you are using a GPU. So for example, I'll also show you here that when we use GPU, which if you remember, you can do from change runtime type, which we'll do. It runs much faster. So this is a generic code for both CPU and using GPU. It defines the parameters, for example, it defines the temperature, it defines the bond dimension. I was doing some tests yesterday and I just saw that for CPU, it was taking 298 seconds with certain value of bond dimension and number of coarse grading steps. And for GPU, it was just taking 54. We are not going to do this. Probably we'll do 30, which is a little faster. But we can still see the difference between GPU and CPU contractions and computation. This code written generally in that paper 2306 paper I mentioned, we do a lot of different models easing. In this case, I'll just do easing model. And that is why the model has been set to easing. But you can do some other model, doesn't really matter. If we are doing easing model, we know the exact Onsager solution, which is this double integral, which you have to numerically integrate. So we do that. So if we just give it a temperature, it will give us a value of the free energy. And free energy is what we'll compute from tensor network. If everything is correct, they should agree very nicely. This is the SVD routine, which we just saw what it means. This is the coarse graining routine, which we saw. And this is the initial tensor. So if the model is xy, there's some other way of constructing the initial tensor. We don't want to go into this right now because we are not going to do xy model. We just have this easing model, so we can delete all these. H is equal to 0 because that's where I know the exact solution and I want to compare to. Once we have compared h equal to 0, you can go and put anything you want here. You can put 5 or something. So let's start with h equal to 0. You can also do it for Potts model, as I said. We are not going to do it, so let's just remove it. Okay, so this is the initial tensor. Once you have the initial tensor, we just compute the initial norm, which is maximum of tensor t. And then we start the number of coarse graining steps we want to do. So for example, if you want to do 10 steps of coarse graining, which is n iterations is equal to 10, we'll do the same thing 10 times. For example, we'll do the coarse graining 10 times. So we'll put in a tensor t, output t and norm, and redo that again. If the model is easing, and then at the end it computes the free energy. So for example, let me see. Yes, at the end of the computation, it will compute the free energy. And once we have the free energy, we can compare using the exact result. So we'll print the exact answer, we'll print our tensor answer, and then print the absolute value of the relative difference between the exact solution and our solution. So this is the plan. For
Sorry,
this,
so you say
yes.
this is like a 30 by 30 lattice, or what lattice?
No. This is let's see.
I missed the 30. That was the bond. Okay.
Bond dimension is 30, number of iterations is 10, so the lattice size is 2 to the 10 times 2 to the 10.
Oh, okay.
Yes.
I see.
Okay. So yes, now we are connected to CPU. Let's just run this for 30 bond dimension, temperature of 2.0. Note that the critical temperature for easing model is around 2.27. So we are below the critical temperature, but we can do it at any temperature. It's just that the errors at critical temperature is much higher. As we saw, the problem with MPS and MERA. These methods are good when you are away from criticality. As you go closer to the critical temperature, the errors, the precision will drop a bit, but it's not too bad in two-dimensional systems. So let me run this. Hopefully it runs without any errors, and we'll see. Okay, it runs. I'm printing some size of the matrices, which you can comment out, which is not needed here probably. So finish 1 step, 2 step, 3 step, 4 step. After 5 steps, it's taking more time because the size has grown now to almost huge. It's 900 by 900, and it's still, so now you see after the 4th step, 3rd step, the tensor size is constant, irrespective of how many times I coarse grain, because that's the uppercut on the bond dimension. So all these will have same, but initially it's start growing from, as you can see, 2 to the 4, 2 to the 4, 4 to the 4, and things like that. Okay, so it finished the computation in 41 seconds. The exact answer is this. Our tensor answer is this, and the difference between the Onsager solution and our tensor computation in 41 seconds is 6.5 e 10 to the minus 7. Right? Now, this number can be further reduced if I increase this or this. And that is something we can explore, but very quickly, in less than an hour, you can go to a precision of 10 to the minus 9, 10 to minus 10 or something. So this is a very powerful method because there's no other numerical method except the MPS based or TRG methods from that. TRG methods are the fastest way of doing, for example, 2D classical statistical system. That is why almost every system we know has been studied using this method, and a lot of new physics about phase transition, critical exponents have been known. The goal, at least for me, is to extend these things in higher dimension, which I'm not going to talk about, but we are working on 3 dimensions right now. So as you probably know, 3 dimensions computing the critical exponents is a very important program with the bootstrap collaboration. So what is the goal there? The goal is to compute the critical exponents of the say 3D easing CFT. So there are only two methods we have today. One is the bootstrap method, one is the Monte Carlo method. And the goal of this tensor program is to go beyond 2 dimensions, because in 2 dimensions we can match everything. Everything works much better with tensors. But higher dimension is more complicated. But if you can go there, the goal is to look at the specific heat scaling and compute alpha, look at the magnetization, compute delta, and compute the scaling dimensions of the CFT, which are related to these exponents, which we get from tensor network. But obviously, the higher dimension, there are different prescriptions of doing coarse graining. Some of them are better than the others, but there are also errors associated. So that is an ongoing research which a lot of groups are working on. Okay, so is there any question at this point? So now what I'll do is I showed that it takes about 42 seconds to run on a CPU. I'll just change this to GPU now. But for that, I probably might have to install something.
Is it, should I assume that if you get closer to the critical temperature, it's going to take longer or something? Or
No, it will not take longer.
the accuracy is going to be.
The time is determined by the bond dimension. So that is not going to take longer, but it will definitely drop in the accuracy. So we can do that test. So for example, let's see, this is this is T, right? So let's see. So just want to make sure something before I start checking that. Yeah, this is temperature. So temperature for easing is 2.27. Let's go closer. So okay, let's make a note of this line here. So this is what we get. Now let's go closer to 2.27. Maybe, yeah, 2.27. If I'm not doing anything wild, the accuracy will drop a bit, but let's check. I have now uncommented those matrix sizes, so it doesn't print anymore. Surprise, surprise. And that's exactly what you see. The error has reduced a bit. Everything is same. The computer, these difference of 3 seconds is just maybe because Google Colab is over. The time is the same. The error inaccuracy goes down, obviously. And this is still at 2.27. If I just want to be more hard on the code, I can I don't remember the exact number in temperature, but the exact number in beta is this. So I can do this, it will drop even further, but that's something which is expected to happen. And I think we have a plot of that in the paper. I think from last year we did that, because one has to show that it like rises on the you can approach from both sides and it rises basically. So even if you go T greater than TC far away, it falls off, tails off. So the errors, the accuracy improves. And at the critical temperatures is the hardest.
So suppose you're given a model that you don't know the critical temperature, or maybe with magnetic field or some totally different thing.
Yeah.
You can use this to find the critical temperature, I guess, like by scanning different temperatures, and then you see something up or something.
Yeah.
Something.
I have a paper on that. I wrote a paper 2 years ago where nothing was known about the POTS model in 3D for Q. So more than 10 state POTS model, there were no numerical results. So with Tensor, I just quickly did Q equal to 11 through Q equal to 20 and found the critical temperature of all of them. Yeah, so it's
more or less this method, of course, more advanced version of this method.
Yes. In the sense that it depends on what kind of, there are other objects we can compute. So for example, in this case, what I would have ideally done is I would have computed it for a range of temperatures and then computed the second derivative of the Z, basically, specific heat. I don't have that plot here, but that's a plot I show at the other lectures where you show that the peak is consistent with the Onsager result, and then you can do it. In fact, based on this, I also have a proposal for a conjectured expression for a finite magnetic field, because as I said, you can do a finite magnetic field very easily here, right? I can just go here and change 1.0, and then it gives me a partition function of free energy corresponding to a finite value of beta and a finite value of h. But that is not known in the literature. But if you do that many times, like try to do some functional fields, and you can try to conjecture some sort of an expression, I think. At least I have been trying to do that. So hopefully I'll write it at some point. Okay. So yeah, so the next thing we want to try was, let's just set it to 2.0, or maybe 2.27 is fine. And then change the run type. We'll now do GPU, and it's some T4 GPU. So there are GPUs of different kinds. For example, ChatGPT uses A100. It's not available right now. We have T4. So we just use T4. It's okay. So now the goal is to see, this was order 37 seconds, 40 seconds. Let's see how much better. It might not be very better because GPU really comes into play when the bond dimension is very high, but we'll do a test here of what is happening. I might have to install some packages. Let's see if I get an error. Okay. No module of times and torches were installed already. Huh. Let's see. This is a problem. Yeah, so the problem is it has to use the what? No module. Okay, so I guess yeah, it might take some time. Let's see if I can do it. It was already there, right? Oh, times and torch. Maybe it was not torch. Or maybe, oh, I changed the runtime. Maybe that spoiled it. Hopefully this should work. But yeah, even if it doesn't work, you know what to do. So this code is, let me share the link for this code. So for example, let me do that. So I'll share the link if you want to play around with this code, play around with Google Colab, want to see the improvement in the contraction. I think most of the things you can do. Here, let's see. So this is the link. So it's, yeah, it's also on GitHub, but this is a Zenodo link where we put so let's see. So this is the link where, which I posted, where we have the code, which I am just using right now. And then it also has the reference and other things. So you can play around with that, I guess. So let's go back and see whether the installation finished. Okay, it finished. Hopefully we'll be able to run this now. Seems to work. Okay, seems to work. So remember that we are looking at 40 seconds. And the computation is done already, 11 seconds. So there's already a factor of 4 using GPU, right? If I increase D to say 90, we saw a factor of 10. So what we could do, like in 30 hours, we just moved the code to PyTorch, made use of GPUs, and we could do it in like less than 4 hours. And that helped us to actually compute the critical exponents of 2D POTS model, 2D XY model much more reliably. Because what happens with critical exponents is we have to be like sitting basically at the critical temperature, and where we saw that the effect of the bond dimension is the highest because the precision goes down. So ideally you want to increase the d as much as you can. But if the computation is slow, increasing d becomes unmanageable. But using GPU, what we could do with d equal to 80, we could do now with d equal to 110. And that really helped us get more precise exponents for two of the models we tried. So for XY model, the critical exponent, for example, is 15. Delta is equal to 15. So delta is just how the magnetization changes around the critical. So magnetization is proportional to H, 1 over delta. So we found that delta is 15. So for example, let's see. Yes, so before going that there, we are convinced that the answer is the same with CPU and GPU, but the timing is a factor of 3.5, close to 4, right? So for example, being a little ambitious, I can probably also do 35 very quickly on GPU. And now this will show you that as you increase the bond dimension, the accuracy becomes better. So let's explore that also since we are on it. The timing will go up, the accuracy will improve, and we'll have the okay, so runs in about 2.23 times. The accuracy has not improved because we went from 30 to, it has changed a bit actually. So, but yeah, if you really want to see the improvement, you have to go into the scaling area. For example, make D 30, 50, 70, and then it'll be more clear. But if you won't do that here, you can explore that. Okay, so that was all I wanted to say about this. Let me, yeah. How much time do I have, Costas?
We started a little bit late, I think, maybe 5 minutes or so.
Okay.
Yeah.
Okay, so in that case, let me see what I can do in 5 minutes. Okay, I think I can do this. Yeah, okay, so let's share the screen. Okay. So now we saw that for, you see the iPad, hopefully.
Yeah.
So we saw that for 2D easing, the initial tensor was 2 to the 4, and then the size increases as we post-clean. For 2D XY model, the initial tensor, you have to trust me this at this point because I cannot drive it. The initial tensor is something like let's not use this notation. Is equal to this. And what is I here? I is just the modified Bessel function of second kind. And what does alpha and beta run from? Alpha, beta, gamma, delta. Unfortunately, they run from minus infinity to infinity. This is the initial tensor. Forget about coarse graining. Just writing the so 2D XY model. I should write down what the action is for that case. The action is just the 2D XY model is just a model on a two-dimensional square lattice you can consider. So a very nice way to look at it is to look at the pages of this notes. They are of the square shape, right? So the lattice is like this, right? Just like the ones of the page, But the important thing is that there is a spin at each site. And that spin can be in any direction. From 0 to 2 pi. And that is my XY model. So I want to write down a tensor description which will explain the model where the spins on each site can be anything between 0 to 2 pi. And this model is very popular because this was the subject of the Nobel Prize in 2016, because this model has very unusual phase transition known as the BKT phase transition. Berezynski, Kostelis, Thouless phase transition. If you remember, Kostas asked whether you can have phase transition when there is continuous symmetry. In fact, Mermin-Wagner theorem says that this model should not have a phase transition because there cannot be any spontaneously broken symmetry with continuous spin model in two-dimension classical. But this model still has one. And that is why this was very unusual. And this transition is related to the topological excitation of vortices and anti-vortices. So this model is what we want to understand, but the major problem, we already hit a roadblock at the starting with the tensors, that the indices are running from -infinity to infinity. So for example, it is this action, this is the initial tensor, but the problem is that we have to truncate at the outset. But we can do that. One important thing to note in this initial tensor decomposition is that the tensor is very smart and knows about the conservation of charges. So what U1, this model is that the reason is that the O2 can be considered in some limit as a U1 spin model also, because there's continuous symmetry on 0 to on a circle. What this says is that there's conservation of U1 charges. That is why alpha plus beta have to be equal to gamma plus delta, right? So for example, alpha, beta, gamma, delta. So for example, what enters is what leaves. And if that is not the case, the tensor element is 0. If only this condition is satisfied, this is obviously zero magnetic field. If you introduce magnetic field, these things changes, because then you don't have any conservation of the U1 is broken. But this is the conservation of U1, this is O2 model, this is the action, and this has a phase transition. So in this model, what you can do is you can compute the magnetization, say for example, as a function of introducing an external field H. And this is a famous exponent for BKT, and for this BKT exponent, this is equal to 15. So for example, using the enhanced GPU methods, we computed this 15 using tensor network methods. But no such computation has yet been achieved in higher dimension. For example, 3D, even for 3D easing model, the critical exponents have not been studied using tensor methods. So definitely not for 3D O2 model. So these are some future directions we have. We want to improve the precision of 2D calculation, go to 3D, and find better coarse graining schemes, because when you go to 3D, what happens is the tensor is something like this, and then you have to then you have these things, and you have to combine 4 of them together, and it becomes really messy. So there are some approximations we have to use in 3D, and those approximations all sometimes fail badly around critical point, and that really prohibits us from computing any sort of critical experiment. Okay, so this was all I wanted to say about real space RG. So in all, I have probably hopefully convinced you that tensor networks, if you ever want to study a lower dimension spin system which is not integrable, which is going to take more time with Monte Carlo or some spin algorithms, Bohr algorithm, and so on, you should go and look at tensor network methods. And they are important for machine learning, quantum computing, and a whole lot of other applications, because the fundamental idea is very simple. It's just tensor. Everything is tensors, and this contraction of that can give you a lot of things you really want in physics. So yeah, thank you for your attention.
Thank you very much. Let's see if there's any questions first from the audience. maybe from the Zoom audience, in case. Okay, so maybe very quickly. So you say that you can reproduce the Kosterlitz-Thouless phase transition.
Yeah.
For X, Y.
Yeah.
Yeah. Okay. So when you see that by some derivatives of the free energy, and you see that.
No, you cannot see that in the derivative of free energy because
it's not a normal phase transition, right? Yeah. So
no,
what?
because, yeah. So you have to the way you can see it is you have to introduce some sort of a. So because of the Mermin-Wagner, there's no magnetization because of there is no long range order in these kind of models. So what you do is you have the O2 model, you can introduce a small symmetry breaking field, and then you compute your magnetization or the susceptibility in that broken U1 theory. And then you take that parameter which breaks the U1 to 0. And in that limit, you extract the critical temperature and you can do all sort of calculations. So you do a calculation on different values of symmetry breaking field, and then you take the limit very delicately and go to that KT phase transition. So we have used that to there are other things you can compute actually. There is something called a helicity modulus and other things people have looked into, but we do it by introducing the symmetry breaking because it's the simplest way of doing it. And we have looked at the critical temperature, we have computed the magnetization with some finite h and computed this delta and several other things. Yes.
Okay, great. All right. I don't see any. Oh yeah, maybe there's a question.
The loss of accuracy, does it always indicate critical temperature? Is that a safe assumption that if you lose accuracy, that means something that's critical?
I guess the question, maybe the question is, if you lose, when you start losing accuracy, is a good indication that you're close to some critical temperature?
Yeah, that can also be, yeah, that's true.
But of course, you need to know the answer to know that you've lost accuracy.
Yeah, exactly. So if you don't know the answer and you are scanning in a wide parameter space and you're doing your tensor network calculations and computing the accuracy with even bond dimension, forget about the exact answer. Just see whether if I change from d equal to 40, d equal to 80, how does the different region of the parameter space changes? If something is not very d dependent, then it's probably an indication that it's not very close to the critical point, because the d dependence will be largest there, because it goes back to the same thing we studied with we saw with MPS and MERA. Around critical exponent, around critical transition, phase transition, everything is, all the information is important. So what you leave during your course training becomes a very subtle issue, and it can really give you a different answer or not precise answer.
Okay. So I think that's it for Raghav's lectures. So let's thank him for this great series of lectures.
Thank you for the invitation. Thank you. I hope it was useful and you learned something.